In this section, we're going to go over what a power series is, how to find the radius and the interval of convergence for a power series, how to define a function as a power series, and then we're going to look at different properties of power series so that we can define other functions that are related to functions. We can define them as power series also. So first, what is a power series? A power series is one where you have just a number times a sub x to a different power. So a sub 1 times x to a 0 power, then x to the 1 power, then x to the 2 power, and so on. That's called a power series in X, and that is a power series centered at 0. Power series can also be centered at numbers other than 0, and so we represent them with the x minus c. And again, this is just some number times that for a power series. So anything of that form where you have x going up in power each time for each term of your series, that's a power series. Basically, a power series in X centered at 0 is just the sum of an infinite number of monomials. So if x equals 0 in a power series that's centered at 0, or if x equals c in a power series that is not centered at 0, it's centered at c, then you get 0 for this part of it, and then 0 to the 0 power we're going to consider to be 1. And so that's why that series is just going to be equal to that first term. So this is an example of a power series in X here. That power series is centered at 0, where 1 over k is just your a sub 0. This series converges to 0 if x equals 0, like we just said in the beginning. And then if x equals 1, we get the harmonic series, which is divergent. If x equals negative 1, then we have the harmonic series, where the alternating harmonic series, where that's going to be convergent. So you can see that we have different cases where this power series, just different cases of X where this power series is convergent or divergent. So what we do to figure out all the numbers in X where a power series is convergent is we use the ratio test. So in this example, this is a power series because, again, we recognize this as x to a power. So it's a power series centered at 0, where we've got this 1 over k to the 1 over k factorial. So if we use the ratio test here, you'll recall that is where we figure out what a sub n is, which is just going to be x to the n power over n factorial, and then a sub n plus 1, which is x to the n plus 1 over n plus 1 factorial. So when we do the ratio test, we do the limit as n approaches infinity, and then we do the absolute value of a sub n plus 1 over a sub n. So I'm going to go ahead and write that as a sub 1 plus n, or n plus 1 over And then I'm going to multiply by the reciprocal of a sub n instead of dividing. So the reciprocal of a sub n is n factorial over x to the n. So from previous sections, we learned that x over n plus 1 over x over n is just x. So we get the absolute value of x. And then n factorial, n plus 1 factorial over n factorial would be just n plus 1, because in those factorials, in n factorial, we're only missing the n plus 1. This is just some number every time. This is a constant depending on what x is. So we can pull that out of the limit. Well, this limit right here goes to 0. So according to the ratio test, that is equal to 0, and if that limit is equal to 0, and if that limit is less than 1, then the series converges absolutely. So this is telling us that no matter what x is, any real number for x that we plug in there, we will get 0 for this limit that's less than 1. So this series converges absolutely for x is equal to all real numbers, or negative infinity to infinity. Basically, it means I can take this particular series, plug any number in, any real number in for x, and that series will converge no matter what x is. In this example, a sub n is n x to the n over 4 to the n, and a sub n plus 1 is n plus 1 x to the n plus 1 over 4 to the n plus 1. So once again, we're going to do the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. So the absolute value only needs to go for the x. So again, I'm going to do a sub n plus 1 times the reciprocal of a sub n instead of dividing them. So I get the absolute value of x to the n plus 1 times n plus 1 over 4 to the n plus 1 multiplied by the reciprocal of a sub n, which is 4 to the n over the absolute value of x times n. Well, 4 to the n over 4 to the n plus 1, we just have one extra 4 here, so those cancel and we get 4 on the bottom. Once again, we can put the absolute value of x on the outside of the limit there. Because again, x to the absolute value of x to the n plus 1 over absolute value of x to the n is just absolute value of x. So I can pull that out. And on top here, I have n plus 1. So that limit is going to be 1/4. So we are left with the absolute value of x times 1/4 over 4. So the absolute value of x over 4 needs to be less than 1, or the absolute value of x needs to be less than 4. Well, for this series to converge, if the absolute value of x is greater than 4, it diverges. But then we have to check what happens at when x is 4 or x is negative 4, because that's not included in these two cases. So if we plug those in, to the original series, and we look what happens when we have x is 4 or x is negative 4 into this original series here. I get 4 over 4, I get 4 squared. So what's happening is these numbers just keep getting bigger. So we can see that the function converges. Same thing, or diverges, I'm sorry, because it just keeps getting bigger, so it's not going to converge to a sum. Same thing for negative 4. If we look at partial sums, if we just look at all the positive cases, that's just going to keep getting bigger. If we look at all the negative cases, that's just going to keep getting bigger, become a bigger negative number. So that also diverges. So both of those diverge. So this series converges absolutely if x is between 4 and negative 4, and then it diverges outside of that interval. For this one, I'm going to use the ratio test again. So a sub n is our n factorial, x to the n, and a sub n plus 1 is n plus 1 factorial, x to the n plus 1. So when we make that ratio, in fact, again, I'm only going to put the absolute value around the x's here. So, because n is always going to be a number bigger than 1, or a positive number, I mean. So here I have n plus 1 factorial, absolute value of x to the n plus 1 power, over n factorial, absolute value of x to the n. This ratio right here just gives us x. This ratio right here gives us n plus 1. And we can pull that absolute value of x out of the limit. That goes to infinity unless x is equal to 0. So if x is not equal to 0, that goes to infinity. And if x equals 0, then we just get 0 for that limit. Because again, we're multiplying 0 by the limit, so that's why we get 0 if x equals 0. So this series only converges if x equals 0, because the ratio test gave us infinity. For anything other than x equals 0, the series diverges everywhere else. So the convergence or divergence of a power series, if the power series converges for any number that's not 0, then it converges absolutely for all numbers x. This is a theorem. As long as that number is less than the original number, the absolute value of that number is less than the original absolute value of the original number. And if a power series diverges for any number x, it diverges for all x's where the absolute value of that number is greater than the absolute value of the original number. So, an example of using those theorems. If I have this series and I know it converges for x equals 6, the absolute value of 3 is less than the absolute value of 6, and therefore it's also going to converge absolutely for x equals 3. Same thing for this idea. Because we know that this series diverges for x equals 4, we're told that, we can conclude that it's also going to diverge for x equals -5 because the absolute value of -5 is greater than the absolute value of 4. So that's just putting these theorems here into practice. That helps us that if we figure out an interval of convergence for a certain series, we can figure out where it's going to converge at other values of x's. We can use those theorems. So for any power series, only one of these is going to be true. Either the series converges only if x equals c, the series converges absolutely for all x, or we have this positive number r for which the series converges absolutely. And we call this r the radius of convergence. From r, we can figure out an interval of convergence because r gives us the radius of convergence from the center. So it's like this length from the center of convergence. And that determines the interval of convergence. So for example, when we did 1b, we figured out that the interval of convergence was -4 to 4. And that was a series that was centered at 0, a power series that was centered at 0. So the radius of convergence was 4, because that's my distance from the center to each interval end. So we can use the ratio test to determine the radius of convergence for a power series and then also the interval of convergence. It doesn't tell us about the endpoints, so just like in that example where we had to plug in -4 and 4 into the series and see what happens, we would do that to figure out the interval of convergence. So the radius of convergence gives us an idea of what the interval convergence is, but it doesn't tell us what happens at those two endpoints, and we have to check that out first before we get that interval of convergence. So in that example 1b, the radius of convergence was 4. We figured out by plugging in -4 and 4 that the series diverged at those values of x, so they are not part of the interval. And so we could figure out that that series converged absolutely in the open interval of -4 to 4. All right, so let's check out this example here. If we're trying to find the radius of convergence and the interval of convergence for this series, we're again going to use the ratio test. So we do a sub n, which is x to the 2n over n, a sub n plus 1, which is x, and then it's 2 times n plus 1, which will make 2n plus 2 over n plus 1. So limit as n approaches infinity of that ratio of a sub n plus 1 over a sub n. I'm going to multiply by the reciprocal of a sub n. So when we look at this, if we think about just plugging numbers in for n, and we have absolute value of x 2n plus 2 over n plus 2, that just means that each of these values, the power is going to be 2 more than the power of this one. So if I did x squared, or x to the third over x, so the power would be 2 more, then I would just subtract those and just get x squared. So that's going to be x squared. I can take away the absolute value because x squared is positive all the time. And that leaves n over n plus 1. So once again, the x squared can come out here. The limit as n approaches infinity of n over n plus 1 is just 1. And so that limit is going to be 1 times x squared, or just x squared. So this converges absolutely if x squared is less than 1. It's our ratio test. It has to converge absolutely if the limit is less than 1. Well, that's the same thing as x is between -1 and 1. So this was a series that was centered at 0. So that tells me that my radius of convergence is 1. Then to find our interval of convergence, we're going to have to test the endpoints, -1 and 1. So if x equals 1, then I have, if we go back to this original summation, x to the 2k over k is the same thing as I'm plugging 1 in for x. So 1 to any power is just 1 over k. That's a harmonic series. And so diverges. If x equals -1, we get the same thing. So therefore, the endpoints are not included in our interval of convergence, and our interval of convergence is -1 to 1. So again, what this means is this series converges if x is between -1 and 1, and it diverges if it's anything else. So this is a good rule of thumb anytime you have a power series and you want to find the interval of convergence. First, use the ratio test to determine the radius of convergence, and that will tell you where the endpoints of the interval of convergence are going to be. Then you're going to test the endpoints by plugging them in to see whether it diverges or converges at each endpoint. And it's possible that it converges at both, that it diverges at both, or that it converges at one and diverges at another. So you need to test both. Once you figure it out, then you make your interval based on whether it converges at those endpoints or it does not. So in this example here, a sub n is going to be -1 to the n power x minus 2 to the n power over n plus 1. A sub n plus 1 is -1 to the n plus 1 power x minus 2 to the n plus 1 power over n minus 2. So I I can ignore this piece of it because of the absolute value. So I'm going to ignore the -1 to the n power in a sub n, and I'm going to ignore the -1 to the n plus 1 power because that's always 1. And then just multiplying by 1, I don't have to write that. So I have absolute value x minus 2 to the n plus 1 power over n plus 2 for my a sub n plus 1. I'm going to multiply by the reciprocal of a sub n. Okay, so here when we look at these ratios, I have x minus 2 to 1 power bigger than this x minus 2. And so if I subtract n plus 1 minus n, I just get 1. So that's x minus 2 to the 1 power. If I have n plus 1 over n plus 2, I can't simplify that. But looking at this ratio for the limit of as n approaches infinity of n plus 1 over n plus 2 is just 1. So then that limit is the absolute value of x minus 2. The absolute value is really important here because that helps us to determine our endpoints. So remember, we want the absolute value of x minus 2 to be less than 1 for this series to converge. Recalling how to solve absolute value inequalities, we change this to x minus 2 is less than 1 or x minus 2 is greater than -1. So this gives us x is less than 3 or x is greater than 1. So again, this is a series. Now this series is centered at 2. Remember, it's always going to be centered at C. So it's centered at 2. My endpoints are 1 and 3. So my radius of convergence is 1. And now I need to test my endpoints 1 and 3. So at x equals 1, we have, going back to this original series here, I'm going to plug into that series here. So I have -1 to the k power in that series, and then 1 minus 2 to the k power. So 1 minus 2 is -1, and then over k plus 1. So this is equal to the sum of -1 to the 2k over k plus 1, because we've got 2 of these. And so since we're squaring -1 no matter, oops, I'm sorry, that should mean 0 to infinity. Since we're squaring -1 no matter what k is, that's the same thing as 1 over k plus 1. That's a harmonic series. That's divergent. So at x equals 1, we're divergent. If x equals 3, I have -1 to the k, and then 3 minus 2 is +1 to the k. So that's equal to an alternating series, harmonic series, which converges. And so it converges at 3. So our interval of convergence includes 3 this time, does not include 1. So we write 3 with a bracket and 1 with a parentheses. All right, now we're going to look at defining a function using a power series. So we can get an equivalent power series and determine what that is as a function. So if f is defined by a power series that has an interval of convergence and x is a number in that interval, then we can say f can be evaluated by finding the sum of that series. So if I want to find, back here, if f of x is equal to this series right here, then I can plug in any number between 1 and 3, and then also I can plug in 3, and I can find the sum of this I can find f of that number by finding the sum of the series at that x. That's what this is saying. So here, to find the domain of f, that's just going to be the interval of convergence for this series right here. That's going to be the domain, because any number that I plug in that interval will work to give me a value for f. So recognize that this is a geometric series. We know that geometric series converge if the absolute value of r is less than 1. So our interval of convergence x would be r in this case. So if the absolute value of x is less than 1, this converges. It diverges at x equals 1 or negative 1. And so our interval of convergence is negative 1 to 1, because that's a geometric series. So that also then is the domain of f. So if I want to find f of 1/2 or f of negative 1/3, then I have to find the sum of the series when x is those values. So for f of 1/2, that means that x, or r, for our geometric series is equal to 1/2. That's in the domain, so we can evaluate that. And the formula for finding the sum of a geometric series is a sub 1, which would be 1 in this case. If I plug in 0 in for k, I get 1. And then 1 minus r. Well, 1 over 1 minus 1/2 is 2. So that means f of 1/2 is 2 if f of x is this power series. We can do the same thing for negative 1/3. That means x is 1/3, or in this case r for our geometric series is negative 1/3. So our sum is, again, a sub 1 is 0. A sub 1 is 1, sorry. 1 minus r. Well, 1 plus negative 1/3 is 1 1/3 or 4/3. 1 over 4/3 is 3/4. So I can find the value of f of negative 1/3 by finding the sum of the series by using the formula for a geometric series to get that is 3/4. So finding f by summing the series means that r is equal to x in my geometric series. So a sub 1 is always 1 in this geometric series. So if I use the formula, we can say that that f has to equal this formula, 1 over 1 minus r, so 1 over 1 minus x, in the interval -1 to 1. So now we have defined what f of x is as a function of x as a series, and then just as a function of x here with a domain of between -1 and 1. So what we're saying is this function, 1 over 1 minus x, is represented by this power series. So in this particular example, we were given a series and we found the function that series represented, and we also found the domain for that function, because that power series only represents that function in this interval. We can also do the opposite. We can find the power series that represents different functions. And because we know this, we can compare each one of these in the next set of examples. We can compare those to the original one, because these are just variations of this. So we can look at what's x being replaced with each time. So in example A, x is replaced by 2x squared. So instead of using the power series x to the k, we're going to use 2x squared to the k. Since the interval of convergence for the original power series was -1 to 1, or the absolute value of x had to be less than 1, we can replace x with 2x squared and say 2x squared has to be, the absolute value of 2x squared has to be less than 1. So this becomes 2x squared is less than 1, or 2x squared is greater than -1. Solving that gives us x is less than the square root of 2 over 2 when I simplify, or x is less than negative square root of 2 over 2. So those are my endpoints. Just like the interval, the endpoints diverged for this original one, that's going to happen here too, though it's going to be divergent at those endpoints. And so, my interval of convergence for this one is the open interval of negative square root of 2 over 2 to square root of 2 over 2. So we can say that in that interval, h of x is represented by that series. We can simplify that series to be 2 to the k, and then x squared to the k. When we distribute that k there. So that function, 1 over 1 minus 2x squared, can be represented by that power series. And again, if I want to evaluate that function at certain values, I can use that sum of that series to do that. This one, this time, we have to change this a little bit. So, because I need to get it so that I have 1 over 1 minus something, and then I can replace x with that something. So algebraically, to do that, we're going to factor out 1/3. And that gives us 1 over 3 times 1/3 is just 1. And then x times 1/3 is 1 over x, or x over 3. This is a plus, so I still don't have it completely in the right form. I need to change it to 1 minus negative x over 3. So that tells me that I can replace x from that original series with negative x over 3. So I can say the absolute value of negative x over 3 must be less than 1, which gives me x over 3 less than 1, or x over 3 is greater than negative 1. I don't need the negative anymore because of this absolute value. So we change that to each of these. So x is less than 3, or x is greater than negative 3. So on the open interval, negative 3 to 3, that function g of x can be represented by the series x to the k, but I'm replacing x with negative x over 3. So negative x over 3 to the k, which is the same thing as negative 1 to the k, and then x over 3 to the k. Sorry, I left off the 1/3. Because of this 1/3 right here, that needs to be in front of our series. We're multiplying 1/3 by that series. Well, now I can put this 1/3 into the series. By saying we have x to the k, and then instead of 3 to the k, I put in this extra 3. I multiply that by 3, so it's like 3 to the 1 times 3, which is just 3 to the k plus 1. So again, if you're just doing a free response, you could stop here. You could leave your series looking like this, but if this is going to be a multiple choice question on the AP, they would most likely have that as their answer. So you would need to recognize that this is the same thing as this. All right, and example C here. This one looks much more complicated because of that x squared on top, but actually it's pretty easy. So in this one, we take out the x squared, and that's all we have to do to get in this form. So here we're thinking, remember that 1 over 1 minus x is just 1 plus x, or when we have that k equals 0 to infinity. That series is just 1 plus x squared plus, and so on. It's just the sum of all those powers. That's why we're calling that the power series. Because we're plugging in that function for different values of k there. So here, f, our capital F of x, is just x squared times that sum. So that just means that in that same interval, this sum right here is the same as, if I multiply that x squared through, I get x squared plus x to the third plus x to the fourth, and so on. So you'll notice that it's this sum, but k isn't starting at 0, k is starting at 2. So instead of using k equals 0 to infinity, we're going to use k equals 2 to infinity of x to the k. So f of x is represented by that sum on the interval, open interval of -1 to 1. All right, the last thing that we're going to look at are some properties of power series. So we have the continuity property, and the continuity property says that the limit as x approaches some number x sub 0 for this power series right here, we can make that into the power series of the limit as x approaches some number x sub 0 of this, which is just this power series with x sub 0 plugged in. That's what the continuity property is saying, as long as x sub 0 is in the interval of convergency. For the differentiation property, this one is saying if we have that particular power series and we take the derivative of that power series, then that we can just use the derivative of this. So remember, the derivative of a power is that we subtract 1 from the power and we multiply by that power. So that's exactly what we're doing here. So the derivative of this series is that series. It's just the sum of the derivative equation there. Same for the integration. We can go backwards. And so the integral of this particular series, we can use the basic integration rule of finding the antiderivative of that series. So we add 1 to the power and then divide by that number, or multiply by the reciprocal. So the way that this is helpful, again, I can use what I know about this one, this series that I know what the interval of convergence is for it, and help me to figure that out and get a representation for this one. So since this is the series that represents that function in the interval of -1 to 1, and if we take the derivative of that, so I can change this to 1 minus x to the -1 power, the derivative of that, if we use the power rule, is -1, 1 minus x to the -2 power, and then by the chain rule, we have to multiply by the derivative of -x, which is -1. Well, that's just 1 over 1 minus x squared. So if this f of x is represented by this series, then I can take the derivative of that series. So f prime of x is going to be represented by the derivative of this series, which is, now we have to put a 1 in here, because you'll notice back here that's going to be k equals 1 for the derivative, because if k equals 0, then I have an x to a negative power, and that doesn't work here. This always has to be 0 and above. This has to be positive, 0 or positive. So we have to change that to k equals 1 to infinity, and then we take the derivative of x to the k, which is k x to the k minus 1. And so that function 1 over 1 minus x quantity squared is represented by this series on the interval open interval -1 to 1. So that's an example of using that derivative property, the differentiation property of the power series. We knew this one. We knew what the representation was for the original function, so we could just take the derivative of that series to get the representation series for the derivative of that function. The next example I'm not going to write out, but I'm going to let you read through this. This is an example of using the integration property, because if I have natural log of 1 over 1 minus x, that happens to be the antiderivative of 1 over 1 minus x. So again, the power series that we know, which is this series, we can use the integral property for. So what they're doing here is they are using that integral property, getting the integration power rule here. So we add 1 to the power and divide by the reciprocal of that. This again is 0. The only reason we had to change it to 1 for the derivative was because that made our power negative, and we can't have that. That's not the case here. So that's going to be our series that represents this antiderivative of 1 over 1 minus x. And again, it's going to have the same radius of convergence as the original one did. To determine the interval of convergence, we don't want to just say that it's exactly the same. We have to check the endpoints. And in this case, you will find that -1 actually converges, because we get an alternating harmonic series. So remember, the harmonic series, that's all positive, diverges, but an alternating harmonic series converges. So we have a bracket for -1. So this function is represented by this series, which we found by using the integration power rule for a power rule, and then we had to plug in the endpoints in order to test the interval of convergence. And then to find the value of the natural log of 2, that means that x is -1 in this function right here. That gives us the natural log of, that gives us negative natural log of 2. So if we let x equal -1 and plug that into the series, then whatever the sum of this alternating harmonic series is, plugging in -1 here, that is what natural log of 2 is. So we can estimate the natural log of 2 if we find a partial sum of that series. And again, the farther out we go, the closer we are to estimating the natural log of 2. In fact, that's exactly what your calculators do when your calculators figure out what the natural log of 2 is they are actually using partial sums of this series to calculate natural log of 2 to so many decimal places.